this one is about unit circle. Let A be a point on the unit circle. I forget about this. I only use X. If B is in X, so it's on the unit circle, and rho AB is 1. Rho is the intrinsic distance, not the second, not the Euclidean distance. Euclidean distance is usually this causes rho sub 2. Rho is the intrinsic distance, meaning that it's along the arc. That arc length is 1, radius is 1, so this angle is 1. This angle is 1. Do you know if cosine 1 is rational number or not? Then prove that B is not in pure square. It is sufficient to prove that cosine 1 is not rational number. Cosine 1 is the, well, without loss of generality, we assume that A is equal to 1, 0. Without loss of generality, assume A is equal to 1, 0. Namely, the point on the x-axis, in the positive x-axis, the circle intersects in a unique point. We take that point, and then 1 goes there. So the x-coordinate of point B is cosine 1. So it suffices to prove that cosine 1 is not a rational number. I can't prove it. Of course, I can't, without citing any famous theorem, I can't prove it. Cosine 1 is not a rational number. Not only so, actually, it was proven that cosine 1 is transcendental number, not even algebraic number. Who proved it? Anyone knows? Famous people proved it. Nowadays we all look at, I don't really like this current politics because everybody only refers to past 6 years papers with their small circle. He did this 5 papers in the last 6 years, and last 6 years. These were something like 600 to 300 years, 100 years old, 200 years old, please. And then if you don't know about who, it was a Fields Medal paper. Lindemann and Weierstrass proved that any linear combination of if you're looking at algebraic number field as ground field, and then look at all real numbers as vectors, then no transcendental number is linearly dependent using coefficients from algebraic numbers. So now let us have a look at what cosine 1 looks like. So cosine 1, this is by Euler. Cosine 1 is equal to, e to the I plus e to the minus I. I is a square root of negative 1 over 2. Where is this? Yes. By Euler. Euler's formula, which says e to the I pi is equal to 1. Right? e to the I pi is 1 is that what Euler's formula says? This is 1 of it. So if you do this, you get cosine 1. That x is what? 1. Now, if you multiply both sides, suppose cosine 1 is a rational number. So if you multiply both sides by 2, what you have is e to the I plus e to the minus I minus 2 cosine 1 is equal to 0. This is a linear combination. This linear combination has coefficients 1, 1, and negative 2. If this is a rational number, if you move it on the other side, so this rational number is equal to the sum of those two one-dimensional numbers. This contradicts this assumption therefore contradicts the Lieberman-Weierstrass theorem. You need to bring out this famous, in my opinion, this is actually a nuclear weapon. I always tease my girl students in South Africa with the following anecdote. You should listen carefully. Girl students in South Africa, they all have a separate room in the hostel. And then I ask her, suppose that South Africa has lots of mosquitoes. Suppose that you have a mosquito in the night so that you can't sleep. You always and try to get. I don't mind getting bitten by a mosquito if it doesn't inject something in me. If it only draws blood, I don't mind. But the thing is that the thing it puts inside you is very. We don't know what it is. Probably scientists don't know, but I don't think they do. You have several weapons in your room. Say you have a TNT bomb. And you have a little needle, which you can actually just go and punch the mosquito if you are precise enough. And you have this Pakistani thing which flaps mosquitoes. And you have a nuclear bomb there as well. If you are using the nuclear bomb, you can definitely be sure that the mosquito will be dead. But who else will be alive there? Even TNT bomb can't. So will you use the... This is like using nuclear bomb to kill a mosquito. This is mosquito, this one. I know girls in South Africa, they usually laugh and can't stop. So this is a nuclear bomb, and you're using this to kill it. By this, we have proved that, and you can actually rotate along the circle. By this we can prove that any point of distance, which is distance 1, from any rational point is no longer a rational point. You can probably prove any rational distance will work. Here there's lots of hidden questions. We see that sine and cosine, we see that 1 is a rational number. Cosine converts into a transcendental number, which is definitely irrational. Sine also does so, but we don't always have this phenomenon. For example, cosine 0 is 1. 0 is rational and 1 is also rational. Question: how often does cosine and sine convert a rational number into irrational? Try to answer this question and you will learn a lot and you might even get a paper. Did you write down the question? Yes. Let us suppose that S is a set of rational numbers which some interval from 0 to 2 pi, 0 is included, 2 pi is not, and so on. And then we look at the set cosine of that's elements of the set. Is it, can you prove that almost every point is converted into irrational numbers? Almost every means that the measure of those points which are not converted is 0. The other measure is 2 pi. The ones which are converted has measure 2 pi, and then ones which are not converted measure 0. even if it is infinitely points, it can be measure zero. Even if it is continuum, it can be measure zero. You know that, right? Because from real analysis or discrete mathematics, counter set has a measure zero, but it's continuum cardinality. Can you prove such a theorem for sine and for cosine? Just say cosine. What happens? The converse. If you're given if cosine is given a transcendental number such as half pi, it converts into zero. The cosine of half pi is zero, right? Cosine of zero is zero. Cosine of pi is zero. So pi and half pi are transcendental numbers. So let us ask the other question. If you are given a set of irrational numbers, what is the measure of measure that cosine converts into rational? This question probably will be easy to answer, but let us just stop here. This is the second question finished. You should ask me questions instead of me just talking to myself. I enjoy it, but because this is what mathematics in my mind is doing. And third question is very easy. This can be an exam question. Let us let x be equal to xy into r squared. X times y is 1. This is one of the manifestations of hyperbola. This hyperbola looks like this. And some of you who submitted converted usually more standard hyperbola looks like that. And then you turn it pi over 4, then you get this hyperbola, right? It is usually in analytic geometry we rotate this pi over 4 and then get the other standard hyperbola. So the students are used to this using the standard hyperbola. Standard hyperbola in this case is x squared minus y squared is 1. Which will be slightly more difficult to work in this question, because this question is very easy now, because we know that x is a rational number if and only if 1 over x is a rational number.
Yes.
If x is non-zero. Only for x equal to 0 it is, we don't need to worry about. We don't worry about that. We forget about that because the domain of definition doesn't go there. So this means that when x is, if x is rational, then y is also rational. If y is x is not rational, then y is also not rational. Sorry, this is not correct. The correct way of saying is if y is rational, then x is also rational. The other one is false. Is it not true? I think. So that means the rational points of this. We can actually write x 1 over x. X is rational. This gives you 2 marks, I think, this question. So this is that question. Next question is about 4. 4 is from the other second set of questions, number 1. So this one I asked when I was progressing, and actually answer is my answer is not good enough. Online answers are even worse. So if you want to memorize online answers, you have to stand for its crime. If it is really not good, then you will not get too many marks from me. My answer doesn't get full mark either, so let us let n be a natural number. Let n be a natural number, and f is a mapping from Euclidean space R into Rn. And if we ask if f is isometry, f is an isometry. If you cannot understand anything, you need to stop me and ask isometry of this space, then f is linear. You have to really go and check all these books. I checked the famous book by Stephen Norman called Advanced Algebra. It doesn't have a few of this. I checked it very carefully. It talks about isometry of metric vector spaces and isometries of metric spaces, and there are lots of things. His style I don't like, although that is probably the best book. I have to tell you, that book has at least one flaw on every page. I can show it to you. That's a very good book, which is a top linear algebra book in English world. The Stephen Norman's Advanced Linear Algebra. And I think you are using it as a textbook here as well. I started examining it, the first 3 chapters are the basic linear algebra. Every page has at least one flaw, in my humble opinion. If I were the editor, I would have rejected that book. Nobody probably read it before the publication, including the author. So that's a pity. For example, this result you cannot find it. This is a vital result, crucial. But there is a mimicking, there's some superfluous thing going on in the internet. This is something about that. Now let us verify about the linear mapping. How do you go about doing this? You know that it's isometric. Not only so, there's another assumption, and F0 is 0. Zero vector is fixed. Even with this condition, you need to prove. Of course, you can go to if 0 is fixed and it is isometry, then this Stephen Norman book says it's an orthogonal transformation. But orthogonal transformations are linear mappings. We didn't assume. You see, when you say orthogonal transformation, you're assuming that it's linear already, and then you prove it's linear. How can there be such a proof? How can there be such a proof? It's linear, therefore it's linear. No. I wouldn't accept that. So isometry in this case, in the Euclidean, this xy now becomes the length of the vector x minus y. The isometry means that f minus fy has the same length as x minus y. Here we did not assume f to be linear. This means that fx minus fy, the length of the image, is equal to the length of the original difference. Of course, the difference is a vector, so length of this vector is equal to length of this vector. I wanted to really discuss with you this Stephen Norman book. I have been going through the first two. I think you're using the your main source, right?
Yeah, they know about it. Stephen Norman's book,
yes.
They are reading.
Every page has a flaw, at least one. You found it, that. At least one flaw, not just some pages have 7 of them. I cannot show you, but I don't want to do that because this guy is still alive, right?
Maybe you are using the old version.
No, it's the new version which I got from the big yellow one.
That yellow one?
Yes.
It has been updated. He has got his YouTube lectures too where he's telling that what are the flaws in there.
You want to test it. This is very strange, huh? I never did this before. So, sorry, my voice is too loud. Okay, please speak more gently. Let me speak more gently. And we know that we assume that F0 is 0. Therefore, from this we can deduce, even without assuming that f is linear or orthogonal, we can deduce that f(x minus f(0) is equal to x minus 0, which is equal to x. And that side is fx. then for this identity says even without assuming that it's orthogonal transformation or linear mapping, only under the assumption that it's isometric, we see that it preserves lengths of vectors.
No.
It preserves norm.
Yes.
Of course, norm to functional analysis double bar, which we didn't use. I think it's not useful. It doesn't matter. And this actually also implies that F preserves inner product.
Yes.
Because Euclidean space has inner product, otherwise it is not called, it is over R and then it has an inner product. Now, these famous internet AI and Stephen Roman now conclude that therefore, and I don't have any saying here, F is linear.
Linear map.
So you need, your task is, which step is not proved yet? It's the last step, this one.
This one is not true.
So your task is to prove that if any mapping preserves the inner product of an Euclidean space, then it is a linear mapping. Of course, the inner product is defined to be bilinear form. But you need to deduce it, even without assuming that F is orthogonal or linear. Because we are doing mathematics, we are not doing science. Scientists can make that jump, let them do. I don't want to make that jump because I will fall. Between there is nothing. I step on. So you need to prove that if any mapping, you need to really assume that it is not any mapping. If any mapping preserves inner product, then it is linear. That is your task. Question 5. Oh, I see. Actually, catches on the next. Question 5. Search the web. I didn't say it. And gather information. This question is probably ridiculous, but I did include it and it's probably not examined. AIs are much better than us in gathering information. Every time when I ask a question with Google AI or ChatGPT, it gives me a very superficial answer. I don't ask any other questions. Other questions, it can give very good answers. For example, who is the boyfriend of Katkin? No problem. He can even tell you that somebody is, but they are no longer together. But in mathematics, the answer was always, in my case, always shallow. I was told by my colleagues that you need to ask and guide it again so that it will do further research. I don't, because I wanted to test its capability. So I just asked the question, and then the answer is just useless for me. So I stopped using it. This information for facility. This is a very suitable question for AI. Facility that uniform continuity provides for analysis. Now I didn't do this, so I have typed the following phrase: simple proof. It is not that. This is another question. This is a question. Let me renumber this. Question 5. I can't see this even in my reading glasses. This is a future question. Question 5 is give a simple proof of counter-Heine theorem. This I searched Google. And it gave a version of Cantor's original proof. And that's fine. So the phrase I typed was a simple proof of counter-Heine theorem. I will not write it. Google search and then it gave you some sort of a proof. You need to be able to understand, but I don't think I'm going to examine this kind of question.
I think that was an Borel theorem, not Cantor.
Counter Borel, that I don't, but one of you actually corrected me. But Borel did actually prove it as well. No, highly Borel.
Yeah.
Highly Borel. Borel is a recent mathematician, actually 20th century mathematician, and Cantor and Heine are 19th century, classified as 19th century mathematician, although they might have died in 20th century. Then we have this question 6. Question 6, I think you have all done. I will just read and sketch the right. So let us take z squared equal to a plus square root of -1, the Gaussian integers, a, b integers. And then you take the u, uppercase u to be the unit vectors, and then the graph can be defined by this z squared and u. We all now know how to define that graph. It's a Cayley graph, locally finite, infinite graph. And then you are supposed to verify that U has 4 elements in it, which is trivial. And you need to verify that 0 is not in it, because 0 has 0, so it is not in it. And then negative of U is U. That needs a very trivial verification. Negative of 1 is negative 1, which is in it. Negative of negative 1 is 1, which is in it, and so on, 4 of them. And then the non-trivial part is the group of isometries that I will write. X. This is X. For that, we go to the graphic. X graphic. Z, U. This group of isometries, you need to prove that it's O n Z. Orthogonal transformation of Z. Z is the ring integral domain. Orthogonal transformation of Z productive with Zn. This Zn contains all the translations by elements of Zn. And that contains reflection and possible finitely many rotations. You should really figure out what this contains, this part. This is question 6. I will go as far as possible so that after coming back, we will go into the actual mini course. Next is question 7. The next question from that in the second batch. Find a non-trivial continuous mapping from X to X. Present. This word is very good because everybody is using this presentation and so on. Present non-trivial continuous mappings. It's very hard to imagine because that space is not a continuous space. No, X to X. If I say N. We just proved that the isometry is a continuous mapping for any. Oh, that was only proved for Euclidean spaces, right?
Yes.
So we cannot really apply that. this is a subring of the Euclidean space.
Mm.
So I certainly found my answers probably correct. What I said was this: any element of this, any non-identity element of this is a continuous, non-trivial continuous mapping, which is probably not correct. You need to decide. So this is openness to me. To me, but we need to redo this question. Question 7. Question 8. Is every continuous mapping from between some metric spaces x, y necessarily contraction mapping or non-expansive mapping? That was our next thing over there. Can this side see this? Let us release the top. Anybody wants to take a picture of this? And then I release.